Radiation is invisible. We cannot see it, hear it, or smell it. Yet scientists can detect it instantly using special instruments. So how do these devices reveal something completely invisible? In this episode, we explore how radiation detection actually works. Radiation gives no direct warning to human senses. A radioactive source may look completely normal, but radiation still interacts with matter. It can ionize atoms, release charge, and produce light, and those interactions become the basis of detection. All radiation detectors follow the same basic idea. Radiation enters a material, the material responds physically, and that response becomes a measurable signal. The detector is essentially translating invisible radiation into visible information. One major effect of radiation is ionization. Radiation can knock electrons away from atoms, creating charged particles. Inside a detector, these charges generate electrical signals. So the detector measures the ionization caused by radiation. The Geiger counter is the world's most famous radiation detector. Inside the tube is a gas under high voltage. When radiation enters, it ionizes the gas and creates an electrical avalanche. Each event produces a pulse, heard as a click. More clicks usually mean more radiation interactions. Geiger counters are excellent for detecting the presence of radiation, but they cannot accurately tell radiation energy, detailed radiation type, or biological danger. They are great survey instruments, but not precision analyzers. Some materials produce tiny flashes of light when radiation interacts with them. These are called scintillators. The flashes are converted into electrical signals and measured. Scintillation detectors are highly sensitive and widely used in medicine and research. Semiconductor detectors use materials like silicon or germanium. Radiation creates electrical charges directly inside the crystal. These detectors can measure radiation energy very precisely. That makes them extremely important in advanced physics and nuclear spectroscopy. Dosimeters are personal radiation monitoring devices. They measure how much radiation dose a person receives over time. Doctors, researchers, and nuclear workers often wear them for safety. A dosimeter acts like a personal radiation record. Radiation detection is essential in modern society. In hospitals, detectors help create X-rays, CT scans, and cancer treatments. In nuclear facilities, they monitor reactors, contamination, and worker safety. Radiation detection protects both science and humanity. No detector is perfect. Weak radiation signals can be hidden by background noise. Some detectors work better for certain energy ranges than others. Understanding detector limits is critical for accurate measurement and safety. In this episode, we discovered how humans detect something fundamentally invisible. We learned that radiation detectors work by transforming interaction into information. Different technologies use different physical principles: ionization, light emission, semiconductor charge generation, or dose accumulation. But all detectors serve the same ultimate purpose: to detect, to measure, and to protect. From hospitals to nuclear reactors, from scientific laboratories to space missions, radiation detection allows us to safely work with one of the most powerful phenomena in physics. Because once radiation becomes measurable, it becomes understandable.